what was my job market paper, Climate Hazards and Resilience in the Global Car Industry. And this paper basically starts from one fact, right? The IPCC states with very high confidence that with climate change, acute climate hazards are becoming more frequent and more severe, right? And this kind of begs, that economists start thinking about how the society and how the economy can adapt to this increase in the probability of extreme weather events. And I'm going to be focusing on how firms can adapt. So I'm going to be focusing on two very specific adaptation mechanisms: an extensive margin mechanism by which firms might modify the location, the number, and capacity of their production sites in response to this increasing likelihood of disasters. Firms can basically modify their spatial organization of production in response to these, changing likelihoods of disaster across the world. And then another adaptation mechanism, which is much more like an intensive margin mechanism by which, conditional on a multinational, multi-plant footprint, firms with multiple plants have the option to switch production from affected or disrupted to undisrupted plants, right? So in this paper, I will try to answer three questions. The first is, basically this idea that I just introduced. How does an increase in the probability of disasters is going to impact the way that firms organize their production in space? Then I'm going to be thinking a little bit about what are the costs of these adaptation mechanisms, right? How much production capacity firms are losing when they adapt? What's the productivity loss of switching production capacity from ex-ante optimal to ex-ante suboptimal places? And then I'm going to be thinking a little bit about how effective is this very narrow adaptation mechanism to spatial organization in reducing the impact of climate change on profits, on the profits of the firms, on consumer surplus, and I'm going to be making a crude welfare computation. So without further ado, let me start. In the interest of time, I will be using data on the car industry as I hinted in the title. Basically, we know that the car industry has very rich data, first of all. Then, it's an industry with multinational, multi-plant firms producing in big physical sites that are susceptible to this type of disasters, where holding inventories is also very expensive. I'm going to be using this data set from IHS Markit, which has been used in different papers in the literature international trade. And basically, this data set has information on new registrations of models, identifying the plant where the car was assembled and the country in which this particular model was sold for the period between 2000 and 2019, and at a high frequency, quarterly frequency. It's important to flag here that they will only have data on the location of assembly, right? But of course, there is a bigger question behind this project that thinks a little bit about supply chains altogether, right? Not only about the last stage of the supply chains. This data set will have information on 77 countries, and will have data on the universe of plants. There are above 1,000 plants in the world during this sample period, and I'm going to append some data on prices for the US, Germany, Japan, Mexico, China, India, and Brazil that I will use essentially to estimate trade costs and a very simple constant elasticity of substitution demand system. So I'm going to use another data set called the Global Archive of Large Flooding Events, which is maintained by the Dartmouth Flood Observatory. And this data has information on very severe floods and contains precise information about the dates of these floods, the geographical location, has measured and different measures of severity of these large flooding events. And this data set exists, it's maintained since 1985. So just to give you an idea of basically where car production takes place in the world and where these floods are occurring, in this map here, the red dots represent a car plant. Basically, we can see that there is a lot of production in the Midwest and the Southeast of the US, in central Mexico, a lot of production in Western Europe. There is production all over China, in Japan, in places in Southeast Asia. And here I'm plotting where floods occurred during the last 20 years. So in the data set, I see two measures of severity. Here, the dark blue dots correspond to 100-year floods, which are floods that are expected to happen in any given year with a 1% probability. And the light blue dots correspond to 10-year floods, which are floods that are expected to happen in any given year with a 10% probability. And basically one of these takeaways is that indeed car plants are right now located in places that might or that do get flooded, right? And you know, this is somewhat expected because we know that these car plants, these big manufacturing sites are certainly located somewhat close to cities, right? And cities in the world usually, you know, lay down in floodplains or close to coasts or to rivers. Now, when I go to the quantitative exercise in the paper, I will be thinking about these firms locating plants in different locations. And here I need to use some sort of administrative units that is subnational, right? Because there's a lot of heterogeneity in the exposure to climate risks within countries. So, you know, for computational reasons, I will be using basically the first level in the hierarchy of administrative units within countries. So states in the US or not one in Europe. Okay, and these ones, the ones highlighted in red, are where we see car production in 2019. Of course, I could go finer, right? But the code and the whole exercise would take a lot more time to complete, right? And in doing this, I will be trying to measure two things that will vary, you know, across these different locations, which will be kind of a measure of labor productivity and a measure of the cost of investing capacity in a particular location. And to measure these things, essentially, what I'm going to do is to project each location into a vector of characteristics, right? Which are these characteristics? Well, I will be constructing for all of these locations, you know, in this bordered by these gray lines, a measure of population, a measure of GDP per capita, a measure of road density, a measure of land availability, and two different measures of bilateral trade costs. One will be tariffs that, of course, vary from country to country, right? And the other one will be distance between each and one of these locations and the population-weighted centroid of each country. And the reason for this is that they only observe sales at the country level, right? So I'm assuming that for, you know, from any of these regions, you can source to the random individual in a particular country. So that's kind of the relevant distance. Now, let me show you the model, which I think it's the main contribution of the paper. Basically, kind of in the big picture, it's going to be a quantitative multi-region model of optimal plant location with capacity investment. So here, firms are choosing two things. They're choosing where to set up their plants, and, you know, they're choosing how much capacity or productive capacity they want to endow, you know, each of their production sites with. Okay, so firms are going to choose these plant capacities to maximize expected profits. So they're doing this kind of with uncertainty about the potential disruptions in the future, right? So they are making their capacity investments today, they're sinking those investments, right? And they know that in the future, these different plant sites that they have decided to build and that they have decided to invest in might be subject to a potential disruption. And in this model, essentially, firms are going to have incentives to invest in production capacity in multiple locations because of two reasons. One is to diversify, right? By having more plants, I am, you know, spreading out kind of my risk in some sense. And the other one is to hedge. And firms in this model might be allowed, or, you know, to invest in capacity in such a way that they might maintain spare capacity in some states of the world that allow them to move production around in response to disruptions. So in this model, this is going to give rise to a proximity, comparative advantage, resilience, if you want, trade-off. And I think that, you know, my application today is going to be climate change and how climate change is going to affect the probability of extreme weather events. But, you know, the model provides a framework to study how changes in the probabilities of the determinants of either, you know, demand or supply might shape how firms organize their production in space. And, you know, you can think about demand volatility, you can think about uncertainty in trade costs, you can think about geopolitical concerns, and the model will be flexible enough, you know, in order to incorporate this type of uncertainty-related concerns. Okay, so what's the model? Basically, I will have J markets, so these markets are going to be countries, and I potential production locations, which are these subnational units within each country. The demand side is going to be conventional. I'm going to assume that firms are monopolistic competitive. I'm going to be assuming that consumers that have a CES demand, that firms have to pay iceberg trade costs in order to ship goods across countries. I'm going to be focusing on industry equilibrium. So I will be taking, you know, car expenditure and wages as given and as fixed, actually, and I will be solving, you know, the equilibrium of the car industry. In this model, firms are going to be potentially multinational and multi-plant, and I say potentially because this is going to be their endogenous choice, And crucially, in each of these plants, they can export, right, which can make or will make their choice of where to set up their plants interdependent, right? They cannot choose where to put their plants in isolation. And the idea, as I told you before, is that firms are going to make investments in capacity, to maximize their expected profits under uncertainty about, potential disruptions that are going to reduce the local productivity, right? And I'm going to assume that capacity investment has a numerical function, but this can be, relaxed. The model can accommodate any, cost function that is weakly convex. And the crucial idea is that after these disruptions are realized, production takes place. So firms can re-optimize, right, exposed, subject to the capacity that they invested on the first place. So I'm going to assume that the production function is going to be linear. We'll only have one factor of production, which will be labor. And the, productivity of this labor is going to be a composite of three things. This phi n, which will be a productivity component that is going to be common across all the plants of the firm. This will capture, let's say, that Toyota is more productive everywhere. This ZIN, that will be a component of productivity that varies at the location, brand level, which will introduce, first of all, comparative advantage, right? Locations within the firm are going to be heterogeneous in their productivity, but it will also give me heterogeneity across different firms producing in the same location. I'm going to assume that the firms are going to know this phi and this z at the time of making their capacity choice. And then I'm going to have this kappa, which will be the disruption, the weather-related disruption. And as I told you before, production is going to be constrained by this c, which is a capacity constraint that is kind of sunk and fixed by the time that production takes place. So firms can re-optimize depending on what are the realizations of these shocks, but this optimization is going to be constrained by the investments on capacity that they did on the first place. So just to fix ideas, firms are born, they know a bunch of things, they know the productivity, they know the cost of investment in each location, they know how big is each market, which I am, denoting by beta J, and they know the productivity draws in each location. Then, with knowledge of this information and rational expectations about the future, I'm going to assume that firms, know the true data generating process for these shocks. Firms are going to choose this capacity investment. And after these disruptions kappa are realized, firms are going to choose quantities in order to maximize profits. And these profits are going to be conditional on this vector C, which is their vector of capacities, and on this epsilon, which is kind of the realized productivity. So how do I solve this model? Let's start by, the ex post profit maximization problem of the firm. So conditional on this vector of productivities, epsilon, which already encodes the disruptions, and this plant capacity C, right, that the firm, chose before. Firms are going to choose essentially quantities in order to maximize profits. And choosing quantities involves choosing how much to ship from each plant to each market, right? So how do firms choose these quantities? By maximizing this function over here. First of all, we have revenues in each market, right? These are production costs that are going to be linear. These disruptions center to this epsilon over here, right? And crucially, without this capacity constraint, this would be a canonical multinationals model. Think about Ramon de Rodriguez, for instance. However, here we have the capacity constraint, right? And this capacity constraint is going to introduce, more richness into the model. And a crucial variable here is going to be this new I. This is going to be the multiplier associated to this capacity constraint. We know that this new I is going to measure for this state of the world, right? And for this level of capacity, what would be the marginal benefit of increasing capacity infinitesimally, right? Or the marginal increase in profits from increasing capacity a little bit. However, this new I also has another interpretation. This new I will be a shallow cost as well, right? And it's basically measuring or capturing what's the cost of producing some goods in a plant that is capacity constrained, that is taking away capacity that might be useful in serving other places, right? We could think, for instance, during the COVID-19 pandemic, these new I's were very, very, very high, right? The cost of this capacity constraint was enormous, right? And actually, these new I's enter the optimal price formula. So the optimal price formula, it's very easy to derive. It's a constant markup, right? Sigma is going to be the elasticity of demand times the marginal cost of serving market J, which is given by the least cost supplier, right? So the firm chooses from all of its locations what's the one that can, serve market J with the least cost. But crucially, these marginal costs are augmented by this new I, right? So this shallow cost is going to be shifting what's the marginal cost of producing in each location. So this is not the problem I've introduced, right? This is a problem, this is an optimal transport problem conditional on capacities. However, I've been talking over and over about the problem of how to choose these capacities, okay? So the problem of the firm, this ex-ante capacity investment problem, is how to, choose capacities in each location in order to maximize these expected profits net of investment costs, right? And generically, you can show that this problem is concave, continuous, and is defined on a set of linear negativity constraints. So it's a conventional optimization problem. On top of that, you can, characterize the problem a little bit further by using the envelope condition to show that the first order condition for investing capacity in location I is equal to this expression over here. So if the firm is indeed investing capacity in a given location, it must be the case that the expected marginal return of investing an extra unit of capacity in this location is equal to the marginal cost, right? So we get this expression that essentially that the expected benefit equals the marginal cost that is conventional in economics. But I want to argue that this condition holds a little bit more of information. First, it's telling us when do we get zeros, right? It's telling us that we're going to get zeros in plant capacity, which of course are a feature of the data. We do not see Toyota or Volkswagen producing everywhere, right? They produce in 10 or 15 plants around the world, and we have much more plant locations. We're going to get zeros whenever the expected benefit of adding or of moving from 0 to epsilon, let's say, it's smaller than the marginal cost, right? So this marginal cost acts like a choke in some sense, okay, or like a hurdle that the minimal profit, like a hurdle for minimal profitability when moving from 0 to epsilon. This is why this imposes another restriction on the cost function for capacity, which is essentially that I need to match the data that the marginal cost of capacity at 0 is equal to something positive. Now, I want to argue that this also has an interesting insight, right? We know from the math camp that these multipliers are positive whenever capacity is binding, right? And this first order condition is telling us that, the if we are setting up capacity in location I, it must be the case that the expected value of nu is equal to something positive. So this is telling us that whenever the firm is opening up a plant, it must be the case that there is a measure or a set of states of the world for which the plant is using this, for which the firm is using this plant at capacity, right? So in this model, with these assumptions, there is no such thing as a plant having a spare capacity always. It might have a spare capacity in some realizations of the shocks, but not always. It must be that there is, at least one state of the world in which, the firm is using this plant fully. So in this sense, there is no wasteful investment in this model, although there is a spare capacity on average. Now, this model is going to be very flexible, and as I told you before, it can accommodate shocks in different places. And the reason for this is that I am going to handle this expectation by simulation, right? And since I'm using a simulation-based approach to measure that expectation, there are no constraints on the set of distributions that I need to use or the place in which I can put the shock. I'm going to put this shock on the productivities, but as I told you before, I could put it on the betas, which are market sizes, or in the taus that are trade costs, right? And the idea, or one of the main innovations of the paper, is that I can solve this problem, first of all, computing the dual of this primal problem, and second, by recasting it as a linear function on a convex set. Just let me say that when I write this, on a linear way, I can handle lots of locations and lots of markets and lots of simulations in a few seconds. So in that sense, the model is going to be quite tractable, but do not let me go over the particular derivations. Just let me say that it's, very flexible, and it could accommodate, different distributions of these shocks in different places in a way connected to the discussion that we've had throughout the day. Now, in this model, I need to estimate a bunch of things. I need to estimate trade cost, I need to estimate a demand function, right? And I need to estimate what are the features of these Cs, these productivities that are firm location specific, and of this capacity cost that are as well firm location specific. And I need to tell you something about how do I map these damages from weather-related disruptions into the model, right? So the first thing, these parameters in red, I'm going to essentially estimate them by using the price and demand equation from the model. And then regarding these these and these alphas, I'm going to basically use a simulation-based method. So I'm going to map basically a distribution for these Cs and alphas on the characteristics that I mentioned before, and I'm going to estimate those in order to match that geography of car plants and production that we see, on the data. Now, let me be a little bit more specific about the disruptions. So how do I think about disruptions? What do I think about this vector kappa? So I'm going to think that these weather disruptions are going to follow a discrete probability distribution that's going to have 3 points of support. Remember that in the data set about floods, I see, 10-year floods and 100-year floods, and I want to maintain essentially or introduce this in the model in a symmetric way. So I'm going to assume that this distribution has, a 3-point discrete distribution. So this kappa 1, let's think about 100-year floods happen with some probability Ri. These 10-year floods happen with some probability Si, and decrease production or imply a damage equal to kappa 2, and with some probability nothing happens, right? I'm going to, in this main exercise, assume independence across locations, but also in the paper, I explore what happens if these shocks are realized with some spatial correlation. And I'm going to estimate this kappa 1 and kappa 2 to match the long-run causal impacts of floods on plant production. So what are these? Basically, here I'm showing you 3 event studies coming from state-of-the-art diff and diff estimators. Basically, here I'm computing what's the effect on production at the plant level, and this is in quantities and total production of the plant level, of experiencing a flood that is occurring nearby the plant. So this is the effect for all floods, this is the effect for 100-year floods, and this is the effect for 10-year floods. And we see indeed that whenever one of these floods occurs close to a plant, there is a quite substantial effect, right? So let me interpret the first one. We see that whenever there is a flood close to a plant, total production declines by around 0.34 log points in a very negative and persistent way. Okay, and these are kind of the moments that I'm going to match in order to estimate this kappa 1 and this kappa 2. So how do I estimate the model, and then I do some counterfactuals. What's the main counterfactual? Basically, I'm going to change the distribution of disruptions, allowing firms to potentially re-optimize their plant organization, right, in response to this changing probability distribution of disruptions. To discipline the changes in the probability, distribution of disruptions, I'm going to use predicted probabilities from the IPCC for historical 10-year and 100-year extreme precipitation events. And I'm going to show you basically the results that are in line with the no policy worst case scenario, right? In the paper, you can see, results for different scenarios. So how are these probabilities changing around the world? As a benchmark, think of these 10-year events happening in each location with a 10% probability, and these 100-year events happening in each place with a 1% probability. We see that 10-year events become 1.5 times as likely, whereas 100-year events are becoming twice as likely on average, right? But we see a lot of heterogeneity, right? For instance, there are some places in Central Africa in which these 10-year events are becoming 2-year events, or these 100-year events are becoming 10-year events, right? So there is a lot of heterogeneity in these changes in the probability disruptions around the world. Okay, so this is the main exercise that I'm going to do. Basically, let's focus on the middle and last columns. The middle column is the one that I use for estimation, right? This is if you want, the current risk landscape, and we can think of this SSP5 as the one in which these expected probabilities of disasters are changing accordingly to the worst case scenario. So we see that in response to climate change, let's say, firms are going to increase the average number of plants they're using to produce. Remember, they have incentives to diversify, right? And they have even more incentives when when the probabilities of disruptions get larger. However, firms are going to be losing capacity big time, right? So firms are shrinking. This is, in the end, a negative productivity shock becoming more likely, right? So firms shrinking net, and of course, there is a decline in average capacity per plant, right? Firms also decline, are becoming smaller in terms of profits. So I compute that for the average firm, the decline in profit is of around 4%, right? Even after re-optimizing, right? These are the results in which firms are kind of absorbing these new probabilities and re-optimizing their spatial organization accordingly. And firms start using more spare capacity on average. And they need to hold this spare capacity just because it's what gives them the option to hedge exposed against these shocks, right? What happens thinking about how good is this adaptation in dealing with climate change, one exercise that we can do is to generate the shocks as if there was climate change, right? But holding the film organization, the film spatial organization constant, right? So it's as if films were myopic and weren't re-optimizing, and we can see that in this case the average decline in profit is around 5%. So the share of loss, just by reorganizing their production in space, films can avert, if you want, like 20% of the losses. So there is we can describe a little bit what are the changes in the countries produced around the world. How is the geography of car production changing? I think the exercise is easier to see if we do it within countries. So here, for these 4 countries, I am plotting essentially what are the change in production shares across the different regions. So we see very markedly that in the US, places in the Midwest and the Southeast, especially Michigan and Tennessee, which are the places in which the most cars are produced, are losing production shares, and these are moving towards the center. In Spain, they are moving towards the south, and in Germany and France as well. And of course, here there's a big caveat. I'm focusing on extreme precipitation, right? But if I were to include, extreme temperatures or other sources of secular changes in weather conditions, these plots might look in a different way. For instance, France and Spain are going to become deserts, right, in their south. Now, the key thing here is that, of course, this adaptation is costly, right? So when films reorganize their production, their marginal costs are going to increase. And this is coming because of 2 things. First of all, plants are getting smaller. So if there are no shocks, capacity is binding more often, right? So this drives cost up. And on top of that, firms are moving to places that have less productivity, right? Like by a rebuild preference type of argument. So marginal cost increased by 7%. Capacity cost on average, barely decrease. And I was hoping to see something larger, but they barely decrease. However, and this is very interesting, so this is on the side of the consumers, okay? When we compute how price indices change in expectation, we see that with film level adaptation, these prices are rising by 2.6%. They're rising everywhere, although with a little bit of heterogeneity, right? However, when films do not adapt, the price indices that these consumers are going to face from the auto industry are going to increase as well by less. So let's start by this case and with this IN. So without film level adaptation, these prices are rising just because these disruptions are getting more and more frequent, right? However, consumers have a very efficient technology, so to speak, in order to hedge against these shocks, right? They can substitute. So if Ford, for instance, receives some sort of disruption, right? Firms can substitute towards GM or towards Toyota or towards, Volkswagen with a small welfare cost, right? So firms, consumers through substitution have a very efficient, let me say, technology in order to adapt to these rising probabilities of shocks that are local, right? They're not completely idiosyncratic, but they're not aggregate. However, when all the firms adapt jointly, right, in the eyes of the consumers, this is like an aggregate shock. So all the firms are doing the same thing. They're holding smaller structures, less productive structures. So all the prices are rising simultaneously for consumers. And this is why when there is this firm level adaptation, consumer prices are increasing. So with this, let me conclude. I showed you basically a framework to think about how the probability of disaster is going to impact the firm's special organization. This is based on the fact that extreme events are becoming more prevalent and severe due to climate change. I showed you that these adaptation mechanisms are very costly. And I showed you that this firm level adaptation through this narrow channel of plan organization is going to buffer the adverse effects of climate change on profits, but it's going to reduce consumer surplus, right? So there is a redistribution or a distributional aspect of investing in resilience, if you want, that is important to think about. That is that in normal times, price indices are on average higher. So with that, I conclude, and I don't know if there are any questions.